Okay, we'll be looking at rate laws and order of reaction today. If you have 2NO, so that's nitric oxide, plus oxygen gas, which gives you 2NO2. The question is, does nitric oxide have a greater effect on the rate of formation of NO2 than oxygen gas? Now, looking at this equation by face value, you might think, oh, because you have 2 here and there's 1 here, that means nitric oxide has more effects on the rate of formation of 2NO2. That means you might think that if you increase the concentration of nitric oxide, you would compare to increasing the concentration of oxygen gas, you will get more NO2. But that is not always the case. The coefficient does not typically reflect how each reactant impacts the formation of products. So we have to determine this empirically. So we have to actually do experiments in the lab where we actually increase the concentration of each reactant independently and see how that impacts the formation of products. So in the case where you have AX plus BY to give you some products, right? The rate of formation of the product is directly proportional to the concentration of X to some power. It can be power 0, power 1, power 2. We indicate that by writing M. The rate of reaction is also directly proportional to Y N. So we can say the rate of reaction is directly proportional to both the concentration of X to the power M and the concentration of Y to the power N. In chemistry, when you see square brackets, we use that to indicate concentration. So in this case, this means concentration of X. Now, if we want to introduce the equal sign here, we would have to also introduce a rate constant. So R is equals to K, that's a rate constant, concentration of X to the power M, concentration of Y to the power N. M and N are exponents that describe the relationship between the rate of reaction and initial concentration of X and Y. Okay, so M and N are exponents that describe the relationship between the rate of reaction and initial concentration of X and Y. So this means that the rate of reaction depends on the exponent M and the exponent N for concentration X and concentration Y. Now these exponents, note, have to be determined via an experiment in the lab. It is not theoretical. And we'll take an example to show that, right? So these exponents M and N have to be determined experimentally, right? What happens is, in the lab, if you have X and Y as both reactants, you will change first of all only the concentration of X and see how that impacts the rate of reaction, and then you change only the concentration of Y and see how that impacts the rate of reaction. And we'll take an example to see that. Now, the general rate law equation is R equals K X to the power M Y to the power N, where K, this is small letter k, is the rate constant for a specific reaction at a specific temperature. That's K. K is the rate constant for a specific reaction at a specific temperature. Right. So, typically, when you are given a question, which we would look at in a bit, there will be two things you'll be asked to determine. One, you'll be asked to determine the rate law for that reaction that you are given, and two, determine the rate constant. Okay, and we'll look at that. So just know this: you'll be asked to determine the rate law for that reaction, and then two, determine the rate constant K. Now, to determine the rate law for that reaction, you have to first A, determine M, and B, determine N. Okay, so you have to determine M and determine N, then you can determine the rate law for that equation. Let's take one example right now. In this equation here, you have bromine gas, you have sulfate ion, you have water, you have proton in solution. Now, you are asked to determine the rate law for this equation, but you are given the details, the values. So the values here for the concentration of the BrO3 minus, initial concentration is 4 molar, so this is molar concentration. Two for HSO3 minus, also molar concentration. You have 6, 3, and then the rate which is the molar concentration per second, is 1.6, 0.8, and 0.2. Okay, so what this means is For the initial concentration of the BrO3 minus, when it's 4 molar concentration and HSO3 minus is 6 molar concentration, the rate of reaction is 1.6. But what we did for this experiment is we reduced the concentration of BrO3 minus to 2 while keeping the concentration of HSO3 minus at 6, and we see that the rate of reaction decreased to 0.8. So the first thing we can do is we can just write the general rate equation, which is RO equals K BrO3 minus to the power M and HSO3 minus to the power N. Now remember I said previously you have to find M to determine the rate law for the reaction. You have to A, find M, B, find N. So let's focus on A. Let's find M. To find M, we have to focus on BrO3 minus, right? That's the reactant that has the exponent M, right? So we look at the concentration where we change. We change it between 1, 2, 3. Between 1 and 2, we changed it, but we did not change HSO3 minus. So we change the concentration by a factor of 2, right? And for the rate also changed by a factor of 2. So coming back to this equation, the rate change by a factor of 2, right? We can ignore K in this case. We're just focusing on BrO3 minus. We did not change HSO3 minus, so we just ignore that. And then this changed by a factor of 2m. So we have 2 is equals to 2m, right? They have the same base. This is same thing as 2 to the power 1. So 1 is equals to m, or m is equals to 1. So we can come here and say m is equals to 1. So now let's look for n. We go back to our equation. To look for m, to look for n rather, we're going to focus on HSO3 minus, where we actually change the concentration in the experiment. So if we look at it, we change the concentration between 1 and 3, but we also change that for BrO3 minus, so that's not a good one to use. We want one where we change it for only HSO3 minus and we did not change it for BrO3 minus. So we look at it between 2 and 3, we change the concentration by a factor of 2, but we did not change it for BrO3 minus, so we want that. And we see the rate change by a factor of 4. So the rate is 4. We can ignore K, we can ignore BrO3 minus. We focus on only HSO3 minus, 2n. So 4 is equals to 2n. Mathematically, one will make these have the same base. So what will the base of 2 be to give you 4? It will be 2 to the power 2 equals 2n. Therefore, n is equals to 2. So for B, n is equals to 2. So based on that, we can write our rate law now as R is equals to K BrO3 minus, what's M? M is 1. HSO3 minus, what's N? N is 2. So this is our rate law. And these, because you have 1 here and 2 here, 1 plus 2 is 3. This is what you call a third order reaction. So this is how we find the rate law for a given reaction. Now we are asked to find K also. So now that we have the rate order, we can simply take this equation and plug in one of the experimental values here. We can use 1, condition 1, right? So you have 4 molar concentration, 6 molar concentration, and 1.6 rate of reaction. So if the rate is 1.6 mole per second, K and BrO3 minus is 4 to the power 1. HSO3 minus is 6 to the power 2, right? Remember, this is molar concentration. So 1.6 molar per second equals K times 4 times 36. Just come to this side, right? If we do that, (1.6 molar per second is equals to 144 molar square K. If you want to make K subject of formula, we divide both sides by 144, right? You divide both sides by 144 molar square. So 1.6 molar per second over 144 K. This cancels this. K is equals to 1.6 1 m cancels 1 m, so you're left with 1 m here. It's equals to 0.011 per molar per second. So this is how we find the rate law and K. So just to recap, to find the rate law, 1, determine m and n, and then 2, use the rate law to find K. All right. In the next video, I'll show a different method to find this without actually looking at the times 2 times 4, just plugging in the values into an equation. Okay.